Tonight, you are sitting inside a hole in space about 2 billion light-years across, and almost no one ever mentioned it to you. Look up, and the stars you can count are not lying to you, but the space around them is thinner than it should be. Roughly 1 part in 5 of the matter that ought to be out there simply is not. That missing fraction is changing what every telescope reads back to us, including how fast the universe seems to be flying apart. We are going to follow that one measurement, slowly, all the way down. Because the more carefully you and I look at the emptiness we live in, the harder it becomes to say where the edge of normal actually is. In 2013, 3 astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie were not hunting for a hole. They were counting galaxies. They pulled together infrared surveys and mapped out how many galaxies sit at each distance from us, working outward in shells the way you might count trees by walking in widening circles around a single spot in a forest. What they were really measuring was density. How much stuff fills each layer of space as you move away from where we stand? The expectation was simple. On large enough scales, the universe is supposed to look the same everywhere. Scoop up a cube of space a few 100 million light-years on a side from over here and another from way over there, and the 2 cubes should hold about the same amount of matter. That sameness is not a casual assumption. It is the floor that modern cosmology is built on. So when you count galaxies in shells around your own position, the number per unit volume should flatten out fast and stay flat. It did not stay flat. Close to us, the galaxy counts came back low, not a little low. The region around the Milky Way runs about 20% under the cosmic average for matter density. And the underdense zone is enormous. The radius they traced is on the order of 1 billion light-years, which makes the whole structure something like 2 billion light-years across. Put a number on that you can hold. Light, leaving one rim of this void, moving at the only speed nothing can beat, would still be traveling for 2 billion years before it reached the far rim. The dinosaurs went extinct 66 million years ago. You would have to stack that entire stretch of time, end to end, about 30 times, just to let light cross the emptiness we live in. They gave it a plain name from their 3 initials, the KBC Void. A desert of matter with our entire neighborhood sitting well inside it. One detail in how they measured it makes the result harder to wave away. They did not weigh the matter directly, because you cannot set a region of space on a scale. They measured the light instead, the total glow of galaxies per unit volume, and compared the nearby glow to the glow much farther out, where the universe should look average. The nearby glow came up short, and the shortfall grew the closer they looked to home, which is exactly the pattern a hole would make. If our region were merely poorly surveyed, the deficit would scatter randomly with distance. Instead, it deepened toward us in an orderly way, the signature of a real bowl in the density of space, not a patchy map. That orderliness is what turned a low galaxy count into a claim about the actual shape of the cosmos around you and me. Counting galaxies is not the same as counting matter. Most of the matter in the universe is dark, and on top of that, the dim, small galaxies are the easiest ones to miss at great distances. So maybe the void is not a real shortage of stuff. Maybe it is a shortage of galaxies bright enough for our instruments to register, and we have mistaken our own blindness for an empty room. That objection is exactly the right one, and it is the reason this single finding did not settle anything in 2013. But the shortfall showed up across different ways of looking. It was not only the optical galaxies that ran thin. Infrared counts, which catch cooler and dustier galaxies, told the same story. And the deficit was not a narrow dip you could blame on one bad patch of sky. It held across a huge span of directions, which is hard to fake with a simple counting error. When several independent methods, each blind in a different way, all undercount in the same region, the simplest explanation stops being, "Our telescopes are bad here," and starts being, "There is truly less here." For most of the last century, the guiding instinct in astronomy was that our location is unremarkable. We are not at the center of the solar system, not at the center of the galaxy, not at any special place in the cosmos. That instinct has been right so many times that betting against it feels reckless. And yet, the galaxy counts are quietly suggesting that the patch of universe holding us is not average. It is one of the emptier places, and we appear to be a long way inside it. We have had telescopes for 4 centuries. We mapped the surface of Mars before we noticed that our entire cosmic neighborhood is sitting in a region 20% below the average density of everything. And the reason is almost embarrassingly human. You cannot see the shape of a room from inside it by looking at any single wall. You have to count every wall, in every direction, and compare. The void is not hidden behind anything. It is simply too big and too close for a single glance to register. So we are left holding 2 facts that do not sit comfortably together. The first is that the universe is supposed to be uniform on these scales. The second is that the actual count of what surrounds us comes back low, again and again, no matter which instrument does the counting. One of those 2 has to give. And if the shortage is real, if we truly live in a desert and not just a poorly lit room, then there is a quieter problem waiting underneath it. Every measurement we make of the wider universe is taken from in here, from inside the thin patch. And if the ground you are standing on is not average, how would you ever know it from the readings on your own instruments? 2 completely different methods are supposed to agree on one number, and they refuse to. It is the Hubble constant. Measure it one way, you get one answer. Measure it another way, you get a different answer. And the gap between them has only grown sharper the more careful everyone gets. Take the faint glow left over from the early universe. The light that has been traveling since the cosmos was about 380,000 years old. That light carries a frozen pattern in it, a kind of cosmic baby photo, and the spacing of features in that pattern tells you how fast space should be expanding today if you start from the early universe and run the standard physics forward. That method lands near 67 kilometers per second for every megaparsec of distance, about 67 kilometers per second faster for every 3.25 million light years you move out. Now the other version. Forget the early universe and just watch the nearby one. Pick galaxies whose distances we can measure directly, using stars that pulse at a rate tied to their brightness and using a particular kind of stellar explosion that always detonates with nearly the same energy. Measure how fast those galaxies are receding, divide by how far away they are, and you read off the expansion rate in our own backyard. That method lands closer to 73. 67 versus 73. It sounds like a rounding squabble. It is not. The error bars on both numbers have shrunk so much that they no longer overlap. The disagreement sits at a confidence level where the odds of it being a fluke are smaller than 1 in a million. 2 of the best measured numbers in all of physics, describing the same universe, do not match. People call it the Hubble tension, which is a polite word for a crack in the foundation. You can read that crack 2 ways, and which way you choose changes everything. The first reading. One of the measurements is quietly wrong. Some star we use as a distance marker is not as standard as we think. Some systematic error is hiding in the ladder of distances. People have hunted for that error for years and keep not finding it. The second reading is stranger. What if both measurements are correct, and the universe really does seem to expand faster nearby than the early universe physics predicts? Picture what a void does to a measurement of expansion. If we sit inside a region with less matter than average, then the denser walls of normal universe surrounding us pull outward on everything in here, gently, in every direction. Galaxies near us are not only carried apart by the real stretching of space, they are also drifting toward the richer regions outside the void. Both motions look the same to a telescope. Both show up as redshift, as recession. So when we measure the local expansion rate, we are reading the true cosmic stretching, plus an extra outward drift caused by living in a hole. The number comes out too high. We are not necessarily measuring wrong. Our instruments may be working perfectly, our distance ladder may be sound, and the local number may truly be 73. It is just that 73 might be the local number, a reading distorted by our address, not a property of the whole universe. The early universe number, 67, would then be the honest global value, because that light comes from far outside our little desert and never had to climb out of it. It helps to see why these two methods were ever supposed to agree in the first place. They start from opposite ends of cosmic history and are supposed to meet in the middle. One reads the baby universe and predicts forward. The other reads the grown-up universe and measures directly. For decades, they did roughly agree, within the slop of the measurements, and nobody worried. What changed is precision, as both methods sharpened, with better distance markers on one side and sharper maps of the ancient light on the other. Their error bars shrank, and instead of converging, the two numbers held apart. A disagreement that survives every improvement in precision is the dangerous kind. It cannot be a sloppy measurement because the measurement stopped being sloppy and the gap stayed. That is what moved the Hubble tension from a footnote to a crisis. Not that the numbers differ, but that they refuse to stop differing no matter how carefully we look. If that is true, then the tension is not a failure of physics, it is a failure of location. The equations are fine. We are just standing in a bad spot to take the reading. The way a thermometer held over a candle tells you the truth about the air right above the flame and a lie about the room. But notice what that explanation quietly costs us. To make the void erase the hole tension, the hole has to be deep enough and big enough to add several kilometers per second per megaparsec of fake expansion. And whether a void that large and that empty is even allowed by the standard model of cosmology is very much an open argument, not a settled fix, but a contested one that serious people are still fighting over. So we have traded one problem for a sharper one. Either our best distance measurements are subtly broken in a way no one can find, or we live inside a structure big enough to bend the apparent expansion of the cosmos, a structure the standard model says should be rare. If a void can fake the expansion rate, how empty would the universe have to be, on the largest scales, for emptiness itself to be the rule rather than the exception? Zoom out far enough, and the universe stops looking like scattered stars and starts looking like a sponge. Galaxies do not sit randomly. They string themselves along thin filaments, gather where filaments cross into dense knots, and spread out into flat sheets. And between all of that, sit the voids. Vast, nearly empty rooms, with galaxies smeared across their walls and almost nothing inside. Astronomers call the whole arrangement the cosmic web, and the honest summary is that the universe is mostly the holes. If you tally up where the volume of the universe actually goes, the voids account for somewhere around 80 to 90% of space. The galaxies, the filaments, the bright, glittering structure we point telescopes at, all of it is crowded into the remaining sliver. Imagine a house where everyone you have ever known is jammed into the hallways and the corners, and every actual room stands empty. That is the layout of the cosmos at the largest scale. How did matter end up arranged this way? It traces back to tiny ripples in the density of the very early universe, places that started out a hair denser than average. Gravity is patient and unfair. A region with slightly more matter pulls a little harder, gathers a little more, and that extra mass pulls harder still. The rich get richer. Meanwhile, a region that started a hair underdense loses the competition. Its matter drains toward the denser surroundings, and over billions of years it empties out further and further. Voids are not places where matter was removed. They are places that lost a slow gravitational tug-of-war and kept losing. If voids are the natural outcome of gravity sorting matter, why is the KBC void any kind of problem? Empty regions are expected. The web is supposed to have holes. The trouble is not that a void exists near us. The trouble is the size and the depth of this particular one. Ordinary voids in the cosmic web are tens of millions of light-years across, occasionally a couple hundred million. The KBC void is measured in billions. It is not a typical pore in the sponge. It is one of the largest underdense regions anyone has ever claimed to find, and we are not on its edge. We appear to be reasonably deep inside it. When you and I picture empty space, we imagine a clean vacuum, a perfect nothing. The voids are not that. They still contain dark matter, thinly spread. They still contain a faint web of gas. They still contain the occasional lonely galaxy drifting through. Void does not mean zero. It means a deficit, a region running maybe a third or more below the average density, which over a span of billions of light-years adds up to a staggering amount of missing material. The emptiness is relative, but on these scales, relative emptiness is plenty to bend a measurement. To feel how much a third below average actually removes, scale the whole web down to something you could walk through. Shrink the observable universe until galaxies are like scattered grains of sand in a vast, dark hall. In the dense regions, the grains cluster along ridges and gather thickly at the corners. In a void, you could walk for what feels like a city block in any direction and find almost nothing. A grain here, a grain there, with the nearest ridge of sand far across the room. Now remember, this is not a model on a table. It is the actual layout of everything, and we are standing in one of the emptier stretches of the hall, looking out at ridges of light that are mostly somewhere else. The cosmic web is not a picture of the universe. It is the floor plan of the only home there is, and ours is one of the rooms with the least in it. For a long time, the mental image of where we live was the solar system, then the galaxy, then maybe the local group of galaxies. The web reframes all of that. We are not floating in a representative sample of the universe. We are sitting in one of its great rooms, a low-density chamber bounded by far denser walls we are slowly drifting toward. The matter you are made of, the star it formed around, the galaxy that star sits in, are all riding inside a bubble of below-average density that is itself only one cell in a foam stretching as far as any instrument can reach. The inversion buried in this is the thing I cannot get past. We tend to think of galaxies as the universe and the gaps between them as the absence of the universe. But by volume, the gaps are the universe. The galaxies are the rare exception, the thin residue caught on the walls. If you wanted to describe the cosmos honestly to someone who had never seen it, you would not start with stars. You would start with emptiness, and mention almost as an afterthought that a little matter clings to the edges of it. Everything we know about how the universe expands, how fast, how its history unfolds, we worked it out from inside one of these rooms, using light that mostly crossed other rooms to reach us. We have been reading the architecture of the whole building from a single chamber and assuming the chamber is typical. If we sit in a low-density room with dense walls around us, gravity does not leave us still. The walls pull. So we are not parked here. We are being drawn, slowly and steadily, toward the richer regions outside our void. So before we ask how fast the universe is expanding, there is a closer question. If the emptiness around us is pulling our entire galaxy toward its denser edges, then how much of the motion we attribute to cosmic expansion is really just us? Falling is less than #2. You feel perfectly still right now. You are not. Strip away the spin of the Earth's orbit around the sun's orbit around the galaxy, and there is still a leftover motion underneath all of it, the Milky Way itself, drifting through space at roughly 630 kilometers per second. In the units we drive in, that is over 2 million kilometers per hour. A commercial jet would need around 4 months of non-stop flight just to cover the distance you personally travel, silently, in a single hour of lying in the dark. Astronomers found this motion in a strange place, in the afterglow of the Big Bang. That ancient light should look the same temperature in every direction. It does not, quite. One half of the sky looks a touch warmer, the opposite half a touch cooler. That pattern is a Doppler shift. We are moving toward the warm side and away from the cool side, and the size of the temperature difference tells us exactly how fast, about 600 kilometers per second in a definite direction. The motion is not a theory. It is written across the oldest light there is. The question is, what is pulling us? And the answer used to be something massive out there. A concentration of galaxies whose gravity we are falling toward. There is a real candidate, a dense region nicknamed the Great Attractor, and for years, that was the story. We are sliding downhill toward a pile of mass. But a void changes how you read downhill. Gravity, on these scales, is about contrast. A region that is denser than average pulls you in. A region that is emptier than average effectively pushes you away, not because emptiness exerts a force, but because everything around the emptiness pulls harder than the emptiness does, so the net tug is outward, away from the whole. If we live inside the KBC void, then part of our 600 kilometer per second drift is not us being pulled toward a distant attractor at all. It is us being shoved outward by the underdense desert we sit in toward its denser rim. This matters because the measured motion is too big. The standard model can produce these large-scale flows, but the speeds we actually see run faster and span larger regions than the model comfortably predicts. A real, deep void offers a clean reason. The deeper and wider the hole, the steeper the outward slope, the faster everything inside slides toward the walls. Our awkwardly high velocity stops being awkward and starts being exactly what you would expect if we are deep inside a great emptiness. When a telescope measures a nearby galaxy receding, that recession is a sum, real cosmic expansion, plus the galaxy's own local drift, plus our own drift. Inside a void, those local drifts mostly point outward, away from us, away from the center. So nearby galaxies look like they are running away a little faster than the pure expansion would carry them. The void inflates the local expansion rate not as an abstraction but through this exact mechanism. Real galaxies, really falling toward distant walls, adding their motion to the redshift we read. I want to stay with the size of our own speed for a moment because the number hides how violent it is. 630 kilometers per second means that in the time it takes light to travel 1 second, we have moved 630 kilometers through space. Everyone you love, the planet under you, the Sun, the whole galaxy of a few 100 billion stars, all of it carried in one direction at that speed. And none of us can feel a thing because there is nothing nearby to feel it against. Motion without sensation. We are screaming across the cosmic landscape in total silence. And the destination is the strange part. We are not headed toward anything we will ever arrive at. The walls of the void are billions of light years away, and the universe is expanding faster than we are falling, so we will never reach the rim we are drifting toward. We are in permanent motion toward a place that is itself receding from us, falling forever toward an edge that keeps backing away. You can test whether the void is really doing the pushing, and it comes down to direction. If a massive object were pulling us, our motion should point straight at it, toward the densest concentration of mass in the sky. If a void were pushing us, our motion should point away from the emptiest region, which need not line up with any bright thing at all. When astronomers map both the matter we are falling toward and the emptiness we seem to be falling away from, the push and the pull point in roughly the same overall direction, and that is the clue. It suggests both are real. A dense attractor ahead and an empty repeller behind, working together, adding their effects. Our 600 km/s drift is not one cause winning. It is two causes, pull and push, aligned closely enough that for years we only noticed the pull. That leaves a sharper version of the same puzzle. We can separate, in principle, the part of our motion that is true expansion from the part that is local falling. But to do that cleanly, we need to know the shape and depth of the void we are falling through, and we are trying to map the whole from a position deep inside it. So the next question to address is the issue of scale. If our whole galaxy is just a mote being carried outward inside this desert, then how big does a structure have to be before even a kingdom of 100,000 galaxies counts as a single grain inside the emptiness? The Milky Way belongs to something with a name that means immeasurable heaven. Laniakea, a supercluster of roughly 100,000 galaxies spanning about 500 million light-years. It was mapped in 2014, not by drawing boundaries around where galaxies are, but by tracing where they are flowing. Astronomers measured the motions of thousands of galaxies and asked a simple question: which ones are all drifting toward the same central region? Everything whose flow lines converge on the same basin belongs to the same supercluster. It is a watershed, defined by gravity's drainage, not by walls. 100,000 galaxies. Our own galaxy holds a few 100 billion stars, and the Milky Way is just one member of Laniakea among 100,000. Stack the stars in all of them, and the count runs into numbers the human brain simply refuses to render. More stars than grains of sand on every beach and seabed on Earth, many times over. That is the kingdom we live in. By any human measure, it is unimaginably vast. And then the paradox lands. All of that, the entire immeasurable heaven, 100,000 galaxies 500 million light-years across, fits comfortably inside the KBC void, with room to spare. The void is around 2 billion light-years across. You could line up 4 Laniakeas across its diameter and still not reach the far wall. Our greatest known structure, the thing that contains everything we have ever called home, is a wisp inside the desert, a bright crumb in a mostly empty room. You should resist this for a second, because it sounds like a trick of words. How can a region packed with 100,000 galaxies be called part of a desert? The answer is that density is an average over volume, and the volume here is monstrous. Laniakea is dense compared to the gaps between galaxies. but spread its mass across the full 2 billion light-year span of the void, and the average still comes out about 20% below the cosmic norm. The supercluster is a local concentration floating in a globally underfilled region. Both things are true at once. We live in a rich neighborhood inside a poor county. The way Laniakea was actually mapped changes what the word structure even means. The astronomers did not draw lines around clumps of light. They measured the velocity of every galaxy they could, subtracted off the smooth expansion of space, and kept only the leftover motion, the part caused by gravity tugging each galaxy toward nearby mass. Then they drew the flow lines, the streams those motions trace, and watched where they converged. Everything whose flow drains toward the same basin, they called one supercluster. So Laniakea is not defined by where galaxies are. It is defined by where they are going. Our home is a watershed, and like a watershed on Earth, its boundary stays invisible until you follow the direction the water runs. We belong to Laniakea, not because of a wall around us, but because we are all sliding toward the same low point. The quiet vertigo is in this. The flows that define our supercluster are the same flows that reveal we are sliding through a void toward its denser walls. The map that told us where home is drawn from the very motion that tells us home is not standing still. We did not find a fixed address. We found a current, and we found ourselves carried in it, along with every galaxy we can call a neighbor. The thing that makes us a community, that shared direction of fall, is also the thing that guarantees the community is temporary. This rearranges the meaning of Laniakea itself. When it was mapped, the headline was that we finally knew our cosmic address. Here is the supercluster we belong to. Here are its edges. But Laniakea is not a fortress. Its edges are not fixed. It was defined by flow, and the flows are not permanent. The same expansion that carries distant galaxies apart is slowly working against the gravity that holds a supercluster together. And that opens a truly unsettling possibility about our own kingdom. Laniakea is not gravitationally bound as a whole. The galaxies streaming toward its central basin are not locked into it forever. As cosmic expansion accelerates, the outer reaches of the supercluster will be pulled apart faster than gravity can hold them, and the great convergence of flows that defines Laniakea will come undone. The immeasurable heaven is temporary. We gave it a name and a map at roughly the moment in cosmic history when it is large and coherent enough to map, and it will not stay that way. I keep turning over what that does to the idea of home. We found our place in the universe and learned, almost in the same breath, that the place is a passing arrangement inside a far larger emptiness, and that the arrangement itself is loosening. It is the cosmic version of finally reading the map and noticing the map is dissolving at the edges. If Laniakea sits inside the KBC void, is the void itself sitting inside something larger again? The cosmic web is nested. Galaxies cluster into superclusters. Superclusters thread along filaments. Filaments and voids together make up the foam. There is no obvious reason the nesting stops at our void. Larger flows have been detected, coordinated motions of galaxies spanning regions even bigger than Laniakea, hinting that our whole sector is being drawn towards something on a scale we have not fully mapped. So the kingdom is a crumb, and the desert may be a room in a still larger house. Each time we draw a boundary around where we live, a larger structure swallows the boundary. And that nesting carries a question the standard model finds truly hard to answer. If voids this large keep appearing, and we seem to sit deep inside one of the biggest, then how likely was it, by the rules of our own best cosmology, for us to end up here at all? Run the standard model of cosmology forward from the early universe, and you can ask it a direct question. How often does a void as large and as deep as the KBC void show up? The answer that comes back, in some analyses, is brutal. Almost never. The deficit we appear to live in sits far out on the tail of what the model expects. By some estimates, a deviation so extreme that the odds of it arising by chance are smaller than 1 in a million, sometimes quoted as a departure of around 10 standard deviations from the average. In a field where 3 standard deviations is enough to make people nervous, 10 is not a result, it is an alarm. Here is what 10 sigma means in practice. A 5 sigma result, the threshold physicists use to claim a discovery, corresponds to odds of roughly 1 in 3.5 million. 10 sigma is not twice as unlikely. It is unlikelier by a factor so large that if you ran the universe over and over, you would not expect to see it once in any reasonable number of tries. So either we are the cosmic equivalent of winning a lottery that almost no one should ever win, or the model that calls it a lottery is missing something. Those are the 2 doors, and neither is comfortable. Door 1. The void is real, and we truly live in an exceedingly rare place. That collides head-on with the oldest working assumption in astronomy, that our location is nothing special. Copernicus moved us off the center of the solar system. Every step since has pushed the same lesson. Do not assume you are in a privileged spot. A 10 sigma void with us deep inside it says, quietly, that maybe this time we are in a privileged spot, and the discomfort of that is not scientific so much as it is almost moral. We spent 5 centuries learning not to flatter ourselves. Door 2 is less flattering to the model. Maybe the void is not as improbable as the standard model claims, because the standard model is incomplete. The 10 sigma verdict is only as good as the physics used to compute it. If our understanding of how structure forms is missing an ingredient, then the calculation of how rare a big void should be is also wrong, and the void might be perfectly ordinary under better physics. In that reading, the improbability is not telling us we are special, it is telling us our equations are. When you find yourself in an unlikely place and then declare the place important, you might just be fooling yourself with hindsight. Someone wins every lottery. The winner staring at the ticket feels chosen. The math feels nothing. So maybe we are simply the observers who happen to sit in a rare void, no more meaningful than the one raindrop that happens to land on your eyelash out of the billions that miss. That is a fair caution, and on its own it would deflate the whole story. What keeps it from deflating is that the void is not the only anomaly. It does not stand alone. The Hubble tension points at it. The unexpectedly fast large-scale flows point at it. When a single explanation, we live in a large, deep void, would resolve several independent puzzles at once, the "we just got unlucky observers" story gets harder to hold. A coincidence that explains one oddity is a coincidence. A coincidence that explains 3 is a clue. Be precise about what 10 sigma is measuring. It is not a statement about the void. It is a statement about the model. What the calculation says is this: if the standard model of cosmology is exactly right, then a region this large and this empty, with observers sitting deep inside it, should turn up so rarely that we should not expect to find ourselves in one. So the high number is really the model expressing surprise at its own predictions, colliding with where we live. A model that is surprised by reality is doing its job, and that surprise is exactly the signal telling us where to dig. The discomfort is not that the universe broke a rule, It is that our best rulebook assigns near impossible odds to a place we can plainly see we are standing in. The instinct trained into every scientist is to distrust any result that makes us special, because that instinct has saved the field from error after error. But the same instinct, pushed too hard, becomes its own kind of bias, refusing to see a real feature of our location because admitting it feels like vanity. The void asks us to sit in the gap between two failure modes, flattering ourselves and refusing to look. A humbling twist sits underneath door 2. If the void is common and the model is wrong, then the thing that is special is not our address, it is the moment. We happen to be doing cosmology precisely when our measurements have gotten good enough to notice that the model and the universe disagree. Earlier astronomers could not have seen this. The crack was always there. We are simply the first with instruments sharp enough to read it. Either way, the standard model has a number it cannot comfortably produce, sitting right where we live. Special place or incomplete physics, the void forces a choice, and both answers cost us something we were sure of. Emptiness, it turns out, is not just a problem to explain away. It might be the one place in the universe clean enough to watch the force that is tearing everything apart do its work without interference. If you wanted to study the engine driving the universe's expansion, why might the emptiest place be the best laboratory there is? Something is making the expansion of the universe speed up. Not just continue, accelerate. Galaxies are flying apart faster now than they were billions of years ago, and nothing in ordinary matter or gravity can do that. Whatever is responsible, we call it dark energy, and it makes up about 68% of the entire energy budget of the cosmos. More than 2/3 of everything is a force we named before we understood it. A tug of war runs the universe. Gravity pulls matter together. Dark energy pushes space apart. Inside a galaxy or a cluster, gravity wins easily. There is so much matter packed close that its inward pull overwhelms the gentle outward push of dark energy. That is why your body, the Earth, the solar system, the galaxy are not being torn apart right now. Locally, gravity is in charge. So almost everywhere we can easily observe, dark energy is drowned out by the matter around it. We live inside gravity's home court, and from in here, the opposing force is nearly invisible. The voids are the exception. In a region with little matter, gravity has almost nothing to grab, and the outward push of dark energy stops being a whisper under the noise. It becomes the loudest thing in the room. A void is the one kind of place where dark energy is not fighting an uphill battle against dense matter, it is winning, and you can watch it win. The emptiness is not the absence of physics. It is the one stage clear enough to see the dominant force in the universe acting almost alone. This flips the usual instinct about where to look. We point our best telescopes at the bright, busy places, galaxies, clusters, the crowded knots of the cosmic web. But those are exactly the places where dark energy is masked by gravity. If you want to measure the force driving the universe apart, the crowded places are the worst seats in the house. The empty ones are the best. To study the thing that is 2/3 of everything, you go where there is almost nothing. And we happen to live inside one of the largest empty rooms available. The KBC void is not only a problem for our expansion measurements, it is also a natural dark energy laboratory wrapped around our own neighborhood. The voids grow over time, and they grow because dark energy is inflating them faster than the surrounding matter can drain into the walls. Watch how fast a void expands, and you are watching dark energy's strength directly, with very little gravity in the way to confuse the reading. Does dark energy actually behave differently inside a void than anywhere else? The simplest version of the theory says no. Dark energy is the same everywhere, a constant property of space itself, the same push per cubic meter whether that meter is in a galaxy or a desert. If that is right, the void does not change dark energy. It just lets us see the same dark energy more clearly, with the gravitational static turned down. But there are versions of the theory where dark energy is not perfectly constant, where its strength can vary in space or drift over time. And if dark energy can vary, then a void is exactly where the variation would be easiest to catch, because there is nothing else competing to set the pace of expansion. That is the real prize hiding in the emptiness. The single biggest open question about dark energy is whether it is truly constant or quietly changing, because a constant means the universe expands forever at a steady, accelerating clip, while a changing dark energy could mean a very different fate. Recent large surveys of how cosmic structure has grown over billions of years have hinted, tentatively, that dark energy might not be perfectly constant after all. The hint is not settled. It is an argument in progress. But if it holds, the place to confirm it is in the voids, where the signal is loudest. To understand the most powerful, most abundant ingredient in the universe, the advice is to study nothing, to point your instruments at the regions that contain the least, because only there does the dominant force stop hiding. The emptiness is not a gap in the data. The emptiness is the data. Whether dark energy is constant or changing decides how the universe ends. If it is a true constant, the same push per cubic meter for all time, then expansion accelerates forever at a steady rate, and the universe drifts into a cold, slow, endless thinning. If it is weakening, the acceleration could ease, and the far future looks gentler. If it is strengthening, the push could eventually overwhelm even the gravity-holding galaxies, then stars, then atoms together, tearing everything apart in a finale some call the Big Rip. 3 very different endings, and the only way to tell them apart is to measure dark energy's strength precisely over cosmic time. The cleanest place to take that measurement is in the voids, where nothing else is competing to set the pace. The emptiness around us is not just where we live. It is the instrument that will read the ending. It ties our address back to our luck. If we did not live inside a large void, would we have noticed dark energy's behavior as readily? The very location that throws off our expansion measurements may also be the location that gives us the cleanest possible view of what drives expansion in the first place. The problem and the laboratory are the same place. But a force this dominant should leave its mark on more than just nearby galaxies. If a void 2 billion light-years across is being inflated by dark energy, it should do something to any light unlucky enough to pass through it, including the oldest light in existence, the afterglow of the Big Bang. Can a hole in space leave a cold fingerprint on light that has been traveling for nearly 14 billion years? The oldest light in the universe is everywhere around you right now, and it has a temperature. It is the cosmic microwave background, the glow released when the universe was about 380,000 years old, cooled by expansion down to a couple of degrees above absolute zero. It fills the whole sky, and across that sky its temperature is astonishingly even, the same to about 1 part in 100,000 in every direction. But the tiny departures from perfect evenness are where the information lives, and one kind of departure has a void's fingerprint on it. To see how, follow a single photon of that ancient light as it crosses a void on its way to us. As the photon falls into the void, It picks up a little energy, the way a ball rolling into a valley picks up speed. Then it has to climb back out the far side, which costs energy, the way the ball slows climbing back up. In a static universe, the climb out exactly cancels the fall in, and the photon leaves with the same energy it entered, no mark left. But our universe is not static. While the photon is inside, the void is growing, stretched wider by dark energy during the millions of years the crossing takes. So the wall the photon has to climb on the way out is slightly shallower than the one it fell down on the way in, because the whole region got bigger and shallower while it was passing through. The climb out costs a little less than the fall in paid. The photon leaves with slightly less energy than it arrived with. Less energy stretches the wavelength, and a longer wavelength reads as cooler light. The void stamps a faint cold spot onto the ancient light. This is the integrated Sachs-Wolf effect, and it is a direct bridge between the largest empty regions and the oldest light there is. The cold imprint of void leaves is small, much smaller than the ordinary ripples already in the background light. You cannot point at one cold patch and declare a void underneath it, because random fluctuations make cold patches too. The way you actually detect the effect is statistical. Take many known voids, stack the patches of ancient light behind them, and average. The random ripples wash out, and what remains is a faint, shared cold signal, the collective fingerprint of emptiness on the echo of the Big Bang. That stacking has been done, and the cold signal is there. This is what makes the effect more than a curiosity. It connects two things separated by almost the entire age of the universe. The light was released over 13 billion years ago. The voids that mark it are part of the recent, local structure of the cosmos. When we read the cold imprint, we are watching the youngest large structures write on the oldest light. It also gives us an independent check on the void itself. The KBC void was first claimed from galaxy counts, and galaxy counts can be fooled. But the integrated Sachs-Wolf effect does not care how bright the galaxies are. It responds only to the gravity of the missing mass and to how fast the region is being stretched. If a deep void surrounds us, it should leave a measurable cool tint on the background light coming through it. Finding that tint where the galaxy counts say the void should be turns two separate, fallible methods into one harder-to-dismiss conclusion. The size of this effect tells you something humbling about how gentle gravity is on these scales. The cooling of void imprints on the ancient light is a shift so faint that no single measurement can see it at all. We only recover it by averaging over many voids at once, letting the random noise cancel until the shared whisper survives. Think about that. A structure 2 billion light-years across, draining energy from light for millions of years, and the mark it leaves is almost too small to find. The universe is not subtle because it is small. It is subtle because it is so large that even enormous structures act with an almost unbearable lightness, and we have to listen very hard to hear them at all. A famous puzzle lives right at this intersection. In one patch of the southern sky sits an unusually large, unusually cold region in the background light, colder than the statistics comfortably allow, the CMB cold spot. One leading explanation is that an enormous void lies between us and that patch, chilling the ancient light passing through it by exactly this mechanism. Another explanation is that the cold spot is just a rare fluctuation, an unlucky roll of the early universe dice with no void required. The argument is not settled, but the very fact that a giant void did it is a serious candidate for one of the strangest features in the oldest light tells you how much these empty regions can do. The gentleness of the mechanism is what lingers afterward. No collision, no explosion, no dramatic event. A photon simply spends a few million years crossing a region that is quietly getting bigger and arrives a fraction cooler than it left. The void does not strike the light. It just makes the climb out slightly easier than the fall in. And that tiny imbalance, repeated across a structure billions of light years wide, becomes a signal we can actually detect. The emptiness leaves a fingerprint precisely because it is not empty enough to do nothing. It forces a question back onto our own neighborhood. If voids leave cold marks on light that passes through them, and we live inside a void, then the light from outside reaching us has been climbing out of our own hole for a long time. What does it do to a galaxy to spend its entire existence inside such a place, to be born, to age, and to die in a region this empty? Most galaxies grow up in crowds. They form in dense regions, surrounded by neighbors, and their lives are shaped by collision, mergers that tear them apart and rebuild them, near misses that yank streams of stars into long tails, the constant gravitational shove of a busy neighborhood. A galaxy in a cluster is a city dweller, jostled and reshaped by everyone around it. Void galaxies are not city dwellers. They are the ones born in the desert, with no neighbors close enough to touch. The numbers behind their isolation are hard to feel. Inside our galaxy, the nearest star to the Sun is about 4 light-years away, already a gap so large that the fastest spacecraft we have ever built would take tens of thousands of years to cross it. But a galaxy alone in a void can have its nearest large neighbor tens of millions of light-years away. Scale it down. If a typical galaxy in a cluster is like a house in a dense suburb, a void galaxy is a single house, with no other building visible to the horizon in any direction, and the horizon itself is millions of light-years off. That is not solitude. It is a deeper kind of alone than anything in human experience has a word for. So what does that isolation do to a galaxy? The first surprise is that void galaxies tend to be smaller and bluer than galaxies in crowds. Bluer means younger stars, and younger stars mean active star formation. These galaxies are still making stars at a steady, unhurried pace, while many galaxies in dense clusters have long since stopped, their gas stripped away or used up in violent bursts triggered by their neighbors. The desert galaxy, left undisturbed, sips its gas slowly and keeps forming stars over a much longer stretch of time. That runs against an easy intuition, so follow the mechanism. You might guess that an isolated galaxy, starved of incoming material, would run dry and die young. The opposite happens. In a crowd, galaxies are constantly disturbed, their gas heated, stripped, or slammed into rapid bursts of star formation that exhaust it quickly. Left alone, a galaxy holds onto its gas. Nothing comes along to strip it. Nothing slams it into a frenzy. So it keeps a reservoir of unspent fuel and forms stars gently for far longer than its city cousins. Loneliness, for a galaxy, turns out to be a kind of preservation. A subtler point makes void galaxies scientifically precious. Almost everything we know about how galaxies evolve is tangled up with the effects of their environment, mergers, interactions, the pressure of living in a crowd. It is hard to separate what a galaxy does on its own from what its neighbors do to it. A void galaxy is the clean experiment. It evolves with almost no outside interference, and it shows us how a galaxy grows when nothing is acting on it but its own gravity and its own gas. The isolated ones are the control group for the entire study of galactic life. A fair objection. Maybe void galaxies are not truly untouched, just less touched. Even a void has some structure, faint filaments of gas, the occasional dwarf companion. That is right, and it matters. The isolation is extreme, but not perfect, and the small interactions that do happen in voids are themselves a window into how galaxies behave at the very lowest densities. The point is not that void galaxies live in absolute nothing. It is that they live in the closest thing to nothing the universe offers, and they respond by aging slowly and peacefully. Now bring this home, because we are one of these galaxies. The Milky Way sits inside the KBC void. We are not a perfectly isolated void galaxy. We have our own crowd, the local group, and the larger flow of Laniakea around us. But on the largest scale, our whole neighborhood is a relatively quiet, underdense region, far from the densest, most violent knots of the cosmic web. The Sun has been able to orbit the galactic center for billions of years, steadily, without our galaxy being torn apart by a major collision in that time. The calm that lets stable planets form and life have billions of undisturbed years to develop is, in part, the calm of a quieter corner of the universe. The gas these lonely galaxies carry shows a measurable difference, and it is the cleanest sign of their slow lives. Galaxies in dense clusters often have their gas stripped away as they plow through the hot medium between cluster members, like a runner losing their coat in a headwind. Stripped of fuel, they stop forming stars and slowly redden into old age. Void galaxies face no such headwind. They hold on to their gas, and surveys find them richer in it than their crowded cousins of the same size. That reservoir is why they keep making new stars long after cluster galaxies have gone quiet. A void galaxy is not running out of time. It is the one that got to keep its fuel because nothing came along to take it. The desert, for them, is not deprivation. It is the absence of theft. We imagine the rich, crowded regions of the cosmos are where the action is, and the empty ones are where nothing happens. But for a galaxy, the crowd is where you get torn apart, and the emptiness is where you get to grow old in peace. The desert is not where galaxies go to die. It is where they get to keep living, slowly, long after the city galaxies have burned out. And that reframes the void from a deficit into a kind of shelter. But a shelter from disruption is not the same as a place that makes ordinary sense. If our quiet corner is bending our measurements of expansion, then maybe the problem is not the void at all. Maybe it is the law we use to turn that emptiness into motion. Which opens a heretical question. What if gravity itself does not work the way we think out in the dark? Low density reaches between the galaxies. Almost everything strange we have met so far has been patched with the same two ingredients: dark matter to supply missing gravity, and dark energy to supply missing push. Together, they make up about 95% of the universe, and we have never directly detected either one. We infer them entirely from the fact that gravity, as we currently write it, does not match what we see unless we add them. There is another way to read that mismatch, and it is older and more uncomfortable than most people realize. Maybe nothing is missing. Maybe gravity is the thing we have wrong. The rebellion has a name: Modified Newtonian Dynamics, or MOND, proposed in 1983 by the physicist Mordechai Milgrom. The idea starts from a specific observation. Galaxies rotate too fast at their edges. The outer stars whip around the center so quickly that the visible matter's gravity should not be able to hold them. They ought to fly off. The standard fix is to surround each galaxy with a halo of invisible dark matter, supplying the extra pull. Milgram's fix was different. He noticed that the discrepancy always shows up below a particular, very low acceleration. Above that threshold, ordinary gravity works perfectly. Below it, gravity seems stronger than the equations predict. So Mond proposes a change to the law itself. When the pull of gravity gets extremely weak, weaker than a tiny threshold acceleration, it stops fading the way the standard equations say it should, and instead falls off more gently. That single tweak reproduces the rotation of a huge range of galaxies with startling accuracy, using only the matter we can actually see, no invisible halo required. For galaxies, Mond is not a vague hope. It makes sharp predictions that have repeatedly come true. The objection is immediate and serious, and it has kept Mond a minority view for decades. Dark matter does not only explain galaxy rotation, it explains the way galaxies move inside giant clusters, the way light bends around massive structures, and the detailed pattern of ripples in the background light from the early universe. Mond, in its simple form, struggles with the largest scales, especially clusters, where it still seems to need some extra unseen mass. A theory that triumphs on galaxy scales and stumbles on cluster scales is not a clean replacement. So most cosmologists keep dark matter and treat Mond as an interesting anomaly. In a universe governed by extra gravity at low accelerations, structure forms differently than in the standard picture. Stronger effective gravity in the sparse regions pulls matter out of the underdense zones more aggressively and piles it onto the walls more efficiently. The result is that big, deep voids form more easily and earlier, and large-scale flows run faster. The very things that look like 10 sigma anomalies in the standard model, a void too large, flows too fast, can come out as ordinary, expected features in a Mond-like universe. What is a crisis under one set of laws is a Tuesday under another. That is the quiet power of this rebellion. It does not just offer a different answer to one question. It reframes a whole cluster of separate anomalies: the void's size, the speed of the flows, the local expansion rate, as symptoms of a single thing: gravity behaving differently where matter is thin. And the places where matter is thinnest are exactly the voids, which is to say, exactly where we live. Mond is not a winning theory. It does not explain everything dark matter explains, and most working cosmologists do not accept it as a replacement. But it is also not dead, and the reason it refuses to die is that it keeps making correct predictions about galaxies that the dark matter picture has to fit after the fact rather than predict in advance. A wrong theory should not keep being right about anything. Mond keeps being right about galaxies. Across an enormous range of galaxies, from giant spirals to tiny dwarfs, gas-rich and gas-poor, the speed at which their outskirts rotate is locked to the amount of ordinary visible matter they contain, with almost no scatter. In the dark matter picture, that should be strange. Each galaxy is supposed to have its own invisible halo, and those halos should vary enough to loosen the relationship. Yet the link between visible matter and rotation stays astonishingly tight, as if the visible matter alone sets the motion. That is exactly what a modified law of gravity predicts, and it is what the dark matter picture has to explain after the fact, rather than predict in advance. A tight, unexpected regularity is the kind of thing that makes physicists nervous in a productive way. Nature rarely keeps a promise that precise unless something simple is enforcing it. What unsettles me is the shape of the choice. Either 95% of the universe is made of substances we have never detected, or the law of gravity that we trust completely inside the solar system quietly changes its behavior out in the emptiness where we can least afford to test it. Both options ask us to accept that our confident, everyday physics fails somewhere vast and dark. The disagreement is not about a detail. It is about whether the missing 95% is stuff we cannot see or a law we have not finished writing. And the void sharpens the stakes, because it sits right on the boundary where the two theories disagree most. The deep, low acceleration reaches between galaxies are precisely where dark matter and modified gravity make different predictions. Our address is the testbed for the biggest open question in physics, and we are standing in the middle of it. That uncertainty does not stay contained, though. If we are not sure how gravity works out there, and not sure how fast expansion really runs, then a number we treat as bedrock starts to wobble, the age of the universe itself. Which raises the next question. Could the cosmos be younger than the oldest stars we can see inside it? We say the universe is about 13.8 billion years old, and we say it with confidence. But that number is not measured directly. It is calculated, and the main ingredient in the calculation is the expansion rate. Run the expansion backward, and the rate tells you how long ago everything was packed together at the beginning. A faster expansion rate means the universe reached its current size more quickly, so less time has passed since the start. A faster rate means a younger universe. Now recall the two competing expansion numbers from earlier. The early universe value near 67 and the local value near 73. Those are not just two numbers, they imply two different ages. The lower rate gives the familiar 13.8 billion years. The higher local rate, if you took it as the true global value, would shave roughly a billion years off, pulling the age down towards something closer to 12.7 billion years. A billion years is not a rounding error. It is most of the time it took complex life to arise on Earth. We can measure the ages of stars somewhat independently of the expansion rate, through the physics of how stars burn, and through the slow ticking of radioactive elements forged in them. The oldest stars we have found, in the ancient outskirts of our galaxy, come out around 13 billion years old, with some estimates pushing higher. If the higher expansion rate were the true global value, you would get a universe of about 12.7 billion years, containing stars that are 13 billion years old. The mother younger than her children, a container younger than the things inside it. That is not a tension. That is a contradiction. And a contradiction is the universe telling you that one of your assumptions is simply wrong. So at least one of three things has to give. Maybe the stellar ages are off. Our models of how the oldest stars burn could carry errors large enough to bring them under 12.7 billion years. People have pushed on this hard, and the oldest stars stubbornly stay old. Maybe the high local expansion rate is not the global value, which is exactly what the void explanation has been saying all along. Or maybe the underlying physics we use to convert expansion into age is incomplete. The void offers the cleanest escape, and watch how it resolves the paradox. If 73 is only the local rate, inflated by our living inside an emptiness, then it never should have been used to compute the age of the whole universe in the first place. The honest global rate is the lower one, 67. The universe really is about 13.8 billion years old, and the oldest stars fit inside that age with room to spare. The contradiction dissolves the moment you stop treating a local reading as a global truth. The age paradox is not a problem with time. It is a problem with measuring the universe from inside a hole and forgetting you are inside it. Some of the oldest stars sit in tight ancient swarms called globular clusters, and we read their age from a single turning point. Stars burn through their fuel at a rate that depends sharply on their mass, so the heaviest stars die first. Look at a cluster and find the heaviest star still alive, the one right at the edge of dying, and its mass tells you how long the cluster has been around, because every star heavier than it has already burned out. That clock does not depend on the expansion rate at all. It depends only on the physics of how stars consume their fuel. So when those clusters read about 13 billion years, that number stands on its own legs, which is exactly why a universe younger than them would be a contradiction rather than a curiosity. Could we instead be wrong about the early universe number? Maybe 67 is the mistaken value, and 73 is correct, and the resolution lies in new physics in the early universe rather than a void around us. That is a live possibility, and serious people pursue it. But the early universe number has a quiet advantage. It gives an age that comfortably fits the oldest stars, while the local number does not. When two measurements disagree, and only one of them avoids making the universe younger than its own contents, that asymmetry is a clue about which one to trust as global. A single misread of our location ripples outward, and that is the part of this I keep turning over. Get the expansion rate slightly wrong, and you get the age of everything wrong, and suddenly the stars seem to predate the cosmos. The error does not announce itself as an error. It shows up as a paradox, 3 steps downstream, in a number, the age of the universe, that we had every reason to think was settled. One distorted reading near home, and the entire timeline of existence wobbles. It makes the void's reach feel almost unfair. A region of slightly thinner matter, and it does not just bend a velocity measurement, it threatens the age of time itself, the temperature of the oldest light, the speed of our galaxy, the rarity of our address. One structure, distorting nearly everything we try to measure from inside it. And it feeds a deeper worry about all our instruments. If the void can warp this many readings at once, then maybe the problem is not any single measurement but the vantage point itself. Are we trapped inside a kind of cosmic lens where the whole sky is being distorted before it reaches us? Every measurement of the distant universe is taken from one fixed spot. We cannot travel out and check our readings from a different vantage point. Every conclusion about how fast space expands, how old the cosmos is, how matter is distributed, rests on light arriving at this single location and being interpreted as if this location were typical. The Hubble bubble hypothesis takes that vulnerability seriously and asks a blunt question. What if it is not typical, and we have mistaken the inside of a bubble for the whole universe? The idea is a direct consequence of the void. If we sit inside a region that is underdense, out to 1 billion light-years or more, then within that region, expansion appears faster, for all the reasons we have built up, the outward pull of the denser walls, the local drift adding to redshift. Inside the bubble, the local expansion rate reads high, near 73. Beyond the bubble, out in the average universe, expansion settles to the true global rate, near 67. The tension between the two numbers is then not a tension at all. It is the difference between standing inside the bubble and looking beyond it. This reframes the Hubble tension from a crisis into a geometry problem. The two measurements were never measuring the same thing. The local method samples mostly the inside of our bubble, where the rate is inflated. The early universe method samples the universe as a whole, from light that crossed countless average regions. Of course, they disagree. They are reading two different volumes, and one of those volumes is our distorted home. Under this picture, nobody made a mistake. The numbers are both correct for what they actually measured. If we live in a bubble, The local expansion rate should depend on how far out you look. Measure the rate using only very nearby galaxies, deep inside the bubble, and it should read high. Measure it using galaxies near the bubble's edge and beyond, and the rate should drop toward the global value. A real Hubble bubble leaves a distance-dependent signature, a high rate close in, falling to a lower rate far out, with the transition marking the bubble's wall. If instead the rate stays high no matter how far you look, the bubble cannot be the explanation. Some analyses of the data find hints of just such a fall-off, the local rate easing toward the global value as you survey larger volumes, consistent with a bubble a few billion light-years across. Other analyses do not find a convincing fall-off, and argue the local rate stays stubbornly high even far out, which would mean the tension is real physics, not local geometry. The measurements are hard, the volumes are enormous, and the question of whether the bubble is big enough and deep enough to erase the whole tension is truly open. The Hubble bubble is, in a sense, the comfortable answer. It lets us keep the standard model intact and blame our address instead of our equations. And comfortable answers deserve extra suspicion, because the history of cosmology is full of times the universe turned out to be stranger than the convenient fix. If the bubble is not deep enough, and several studies argue it is not, then we are back to needing new physics, and the void was a distraction from the real problem. We are trying to determine whether our vantage point is distorted using only instruments located at that same vantage point. It is like trying to tell whether your glasses are tinted by looking through them at the world. The bubble hypothesis is testable. The distance dependence gives us a handle, but the test itself is run from inside the very region whose typicality is in question. There is no second Earth, parked in an average part of the universe, to phone home with the unbiased reading. The reason this is not hopeless is that we have many independent rulers, and they do not all share the same blind spot. The local distance ladder, the ancient background light, the frozen sound waves in galaxy clustering, the timing of distant explosions, each leans on different physics and different assumptions. If our location distorted all of them in the same way, we would be lost. But a void distorts some measurements and leaves others nearly untouched because they sample different volumes or respond to different things. So the strategy is to lay all the rulers side by side and ask which combination of true expansion plus local void can fit every one of them at once. It is detective work, not a single reading, and the fact that the rulers mostly agree on a lower global rate, with the local one standing out, is itself the strongest hint that the local one is the distorted member of the family. And that limitation is not a temporary inconvenience. It is permanent. We will never stand outside our own location. Whatever we conclude about the bubble, we conclude it from inside, by cross-checking many indirect methods against each other and hoping their shared answer is the true one. Cosmology is the one science where the laboratory contains the observer, with no exit. So, the question of whether the void is real cannot rest on the expansion rate alone, because that is the very measurement under suspicion. We need a ruler that does not depend on assuming our location is normal, something laid down in the early universe, the same length everywhere, that we can read out at different distances and trust. Does such a ruler exist, frozen into the structure of the cosmos itself? Before there were stars, the universe rang. In the first few 100,000 years, everything was a hot, dense plasma, matter and light locked together, so tightly coupled that a push in one place sent pressure waves rolling outward, exactly like sound moving through air. The early universe was filled with sound. real pressure waves traveling through the primordial fluid at more than half the speed of light. And then, abruptly, the sound froze. Here is what froze it. When the universe cooled to about 3,000 degrees, the plasma turned into neutral gas, and light decoupled from matter and streamed free. That release is the background glow we met earlier. The moment light let go, the pressure that had been driving the sound waves vanished. Each wave that had been expanding outward from a dense spot stopped in its tracks, leaving a shell of slightly higher density frozen at a fixed radius around every original lump. That radius, the distance the sound traveled before it froze, is about 490 million light-years in today's stretched-out universe. It is the same everywhere, set by physics that was identical across the whole cosmos, a standard ruler stamped into the distribution of matter at the dawn of structure. These frozen shells are called baryon acoustic oscillations, and they are the closest thing cosmology has to a tape measure built into reality. Galaxies are very slightly more likely to sit about 490 million light-years apart than at other separations, because they preferentially formed on those frozen shells. Survey millions of galaxies, measure the separations, and a faint preferred distance emerges from the noise, the ruler, showing up statistically in how galaxies cluster. Because we know its true length from early universe physics, we can compare that known length against how large it appears at different distances and read off the geometry and expansion of space without ever assuming our location is typical. The expansion rate measured from nearby galaxies is exactly the number under suspicion of being distorted by our bubble. But the acoustic ruler does not rely on that. It has a known physical length, fixed in the early universe, and it can be measured at many distances. If we live in a local bubble, the ruler should look slightly distorted nearby, stretched or compressed by the void's distortion of distances, and return to its true behavior farther out. The ruler lets us test the bubble using geometry instead of velocity. And what the ruler shows is part of why the picture is contested rather than settled. The acoustic measurements, taken over enormous volumes, tend to agree with the lower expansion rate, the global value near 67, the one that keeps the universe comfortably older than its oldest stars. That supports the idea that the high local rate is a local effect. But the same measurements have not delivered a clean, unambiguous detection of the KBC void's full depth, and some analyses find the local data harder to reconcile with a void large enough to explain everything. The ruler narrows the possibilities without closing the case. How can we trust a ruler we can only see statistically as a faint bump in how galaxies cluster? It is not a line painted across the sky. It is a subtle preference, dug out of millions of galaxy positions. The answer is that its strength comes precisely from being statistical and from being grounded in simple, well-understood early universe physics. The sound waves depend only on the basic ingredients of the young cosmos, which we measure independently from the background light. The ruler is trustworthy, not despite being faint, but because the physics that sets its length is the cleanest physics we have. The chain of survival here is quietly staggering. A pressure wave started rolling through plasma in the first moments of the universe. It traveled for a few 100,000 years, froze when light broke free, and then sat there as a faint overdensity while galaxies formed on it over the next 13 billion years. And now we recover that frozen sound by counting galaxies and use it to measure the shape of space. A sound from before there was anything to hear it, preserved in the arrangement of galaxies, read back as a ruler. This ruler is trusted more than almost any other in cosmology, for one specific reason. Its length is not calibrated against anything nearby. It is set entirely by simple physics in the young universe, how fast pressure waves traveled through the early plasma, and how long they traveled before the plasma turned to gas. Both of those depend only on basic ingredients we measure independently from the ancient light. So unlike a distance ladder, which builds outward step by step and can accumulate error at every rung, the acoustic ruler arrives with its length already known from first principles. That is what lets it cut across the whole tangle. When a ruler whose length we know from the dawn of the universe agrees with the lower expansion rate, it is hard to blame the disagreement on a broken local measurement. The frozen sound does not care where we live. It also reframes what empty means in our region. The void is not silent in the way we imagined. It still carries the frozen echo of that primordial sound, written into how its sparse galaxies are spread. Even the emptiest place we know is marked by the ringing of the early universe. But our void may not be the largest or strangest of its kind. If we want to know whether deep voids are rare flukes or a common feature of the cosmos, we should look for others, and there is one, in the constellation of the River, that may be even more extreme than our own. What would it mean if our void had a darker, older twin? In the southern sky, in the constellation Eridanus, sits a region that may be the largest known empty space in the universe. The Eridanus supervoid is estimated at around 1 billion light-years across, possibly more, and it is unusually deep. If our void is a desert, this one is a deeper desert, and it sits at the heart of one of the most famous puzzles in cosmology. Because the Eridanus supervoid lines up with that strange cold patch in the oldest light, the CMB cold spot. The alignment is what makes it compelling. We met the cold imprint mechanism earlier. Light passing through a growing void leaves with slightly less energy and reads slightly cooler. The cold spot is an unusually large, unusually cold region in the background light, colder than the standard statistics comfortably allow. And sitting between us and that patch of sky is the Eridanus supervoid, exactly where you would want a void to be if a void were responsible for chilling the light. One enormous emptiness, in the right place, draining a measurable amount of energy from the oldest light crossing it. When people calculate how much cooling the Eridanus supervoid should produce, the simplest version comes up short. A void that size, under standard physics, chills the light, but not by quite enough to account for the full depth of the cold spot. So either the void is deeper or larger than the standard estimate, or the standard physics of how voids affect light undercounts the effect, or the cold spot has a second cause stacked on top of the void. The void explains part of the puzzle and leaves part of it open. Some have speculated that the cold spot could be a bruise, a mark left by our universe bumping into another universe in a multiverse, a collision that left a cold dent in our sky. It is a real proposal in the literature, but it is highly speculative, far from established, and most cosmologists regard the giant void explanation, even an imperfect one, as far more likely. The honest status is that we have a large void in the right place that explains much, but not all of the cold spot, and a long tail of more exotic ideas that no one can rule in or out. Set the cold spot aside, though, and the deeper significance of the Eridanus supervoid is what it does to our sense of how rare we are. Remember the 10 sigma problem, the claim that a void as large as the KBC void should almost never exist. That argument rests on these being freak occurrences. But if there is a second supervoid, comparably large, in a completely different part of the sky, then giant voids are not 1 in a billion flukes. They are a recurring feature of the cosmic web. And if they recur, then our void stops being a miracle and starts being an example. The thing that needs explaining is no longer, why are we special, but why does our model say these should be rare when the sky keeps showing them to us? A single huge void deep enough to bend our measurements could be dismissed as cosmic bad luck, a fluke we happen to live in. Two of them, in different directions, turns bad luck into a pattern, and a pattern points at the model rather than at us. The standard model predicts that voids this large should be vanishingly rare. The sky keeps producing them. When prediction and observation diverge that sharply, and the observation repeats, the pressure moves onto the prediction. The two voids change each other's meaning, and that shift is hard to shake. Alone, the KBC void is an anomaly about our address, a question of whether we got unlucky. Paired with Eridanus, it becomes an anomaly about the rules, a question of whether the model that calls big voids rare is simply wrong about how emptiness forms. The same structure, read against a twin, stops being about us and starts being about physics. The bigger and deeper you make these voids to explain the anomalies, the more violently they collide with the standard model's prediction that such voids should be rare. So you cannot have it both ways for free. Either the voids are modest, in which case they explain less of the Hubble tension but sit more comfortably in the model, or they are enormous, in which case they explain more but make the model's rarity prediction look badly wrong. Every attempt to use the void to solve one problem deepens a different one. That is not a flaw in the argument. It is the shape of a real scientific crisis, where the fixes for one anomaly keep generating new anomalies, and no single adjustment quiets the whole system at once. What the twin really changes is the burden of proof. When there was one giant void, the conversation was about us. Were we unlucky? Were we mismeasuring? Were we fooling ourselves? With a second supervoid in a completely different patch of sky, the conversation shifts to the model. Why does our best theory of how matter clumps keep predicting that the largest empty regions should be rarer than the ones we keep finding? A theory is allowed one awkward exception. It is not so easily allowed a repeating pattern it cannot reproduce. Each new supervoid we confirm moves the strangeness one more step away from our address and one step closer to the equations. If giant empty regions are common and matter keeps draining out of them onto the walls, then what happens to structure inside a void over the long run? Do voids simply sit there, or are they slowly filtering and starving the matter caught inside them, shaping a different kind of cosmic evolution than the crowded regions ever see? In the dense regions of the cosmos, structure builds fast and builds big. Galaxies merge into larger galaxies. Galaxies gather into clusters. Clusters draw together into the massive knots where the cosmic web crosses itself. Gravity in a crowd is a runaway process. The more mass collects, the faster it pulls in more. Inside a void, that engine never starts. The matter is too thin and too spread out for gravity to win quickly, so the grand pile-up that happens in dense regions simply does not happen here. Voids are where structure formation stalls. Think of it as a filter, rather than a graveyard at first. A void lets through only the smallest, slowest kind of growth. Big clusters need a lot of matter close together to assemble, and a void never provides it, so the largest structures are filtered out before they can begin. What you get instead are small, isolated galaxies, growing slowly, never gathering into anything grand. The void does not kill structure so much as it never lets it get started, a region permanently stuck at an early, sparse stage while the dense regions race ahead. A second filter is running too, because the void is not static. Matter inside a void is slowly draining out of it, pulled toward the denser walls over billions of years. So a void is not just failing to build, it is gradually emptying further, its already sparse contents migrating toward the edges. Over cosmic time, the inside grows quieter, not busier. The longer a void exists, the more thoroughly it strips itself of the raw material that structure would need. That is the graveyard part. Not violent death, but a slow, steady starvation of possibility. Now turn that around, because there is a strange upside hidden in the stalling. The dense regions, where structure thrives, are also where galaxies are most violently disrupted. Mergers tear galaxies apart and rebuild them. Close passages fling stars into space. The crowded knots are sites of constant gravitational violence. The void, by failing to build big structures, also fails to produce that violence. A galaxy in a void grows slowly, but it also gets left alone. No major mergers, no near collisions, no neighbor close enough to disturb it. The same emptiness that starves growth also grants peace. This is where it touches the question of life. We do not know what conditions life requires beyond the one example we have. But we can say something concrete about disruption. A planetary system needs long stretches of stability to form and persist, billions of years without a nearby catastrophe rearranging everything. In a dense region, the odds of a disruptive encounter over billions of years are higher. In a quiet, underdense region, they are lower. Our own sun has orbited the galactic center for over 4 billion years without our galaxy suffering a major merger in that time, and that long calm is part of why stable planets, and we, are here at all. Voids are not only peaceful, they are poor. The same low density that prevents disruption also means fewer galaxies, fewer stars, fewer chances for anything to happen at all. A place that is safe but nearly empty is not obviously a good place for life. It is a quiet place with very little in it. The advantage of calm has to be weighed against the disadvantage of scarcity, and which one matters more is something we truly cannot answer with one example. We celebrate the dense, dramatic regions, the great clusters, the colliding galaxies, the bright, violent knots, as where the real action is. But action for a galaxy often means destruction. The voids, dismissed as where nothing happens, may be exactly where things get to last. Stability is not the absence of a story. For anything that needs time, stability is the whole story. It reframes our own quiet corner one more time. We have treated the void as a problem, a distortion of our measurements, an anomaly in the model. But the same low density that bends our readings may be part of why we had the undisturbed billions of years it takes to get from the first cells to a creature that can map the void at all. The thing throwing off our instruments may also be the thing that let us build instruments. Voids are almost entirely free of the giant elliptical galaxies and rich clusters that dominate the dense regions. Those massive, red, dead galaxies are the end products of repeated mergers, and mergers need crowds. Without crowds, the void never assembles them, so its galaxies stay small, blue, and disc-shaped, frozen in a sense at an earlier stage of cosmic evolution. Looking into a void is a little like looking into the past, not because the light is older, but because the structures never got the chance to grow up. The dense regions raced ahead into giant, exhausted galaxies. The void stayed young and unfinished. Two regions of the same universe, the same age, living at completely different speeds. Still, peace inside the void does not mean stillness. Even as structure stalls in here, our whole region is in motion. And when astronomers measure those flows carefully, they find they are bigger and more coordinated than the standard model expects. What is pulling such enormous stretches of the universe along together, all in the same direction? We have talked about the Milky Way's own motion. But our galaxy is not drifting alone. When astronomers measure the velocities of galaxies across huge regions of the sky, they find something that should not, by the simplest expectation, be there. Vast numbers of galaxies, spread across hundreds of millions of light years, all drifting in roughly the same direction at once. Not a random scatter of motions, but a coherent flow, like discovering that an entire ocean, not just your boat, is sliding the same way. These coordinated motions are called bulk flows. In the standard picture, galaxies do drift toward nearby concentrations of mass, but those motions should mostly be local and should average out over large enough regions. Sample a big enough volume, and the individual drifts should cancel, leaving only the smooth, even expansion. The bulk flows do not cancel. Across regions hundreds of millions of light-years wide, the average motion stays stubbornly non-zero. Galaxies keep flowing one way faster and farther than the model comfortably predicts. So something large-scale is doing the pulling, and there are competing answers. One is the Great Attractor, a dense concentration of mass a few 100 million light-years away that our local region is falling toward. But the flows seem to extend beyond what the Great Attractor alone can explain. Beyond it lies an even larger concentration, sometimes called the Shapley supercluster, and the flows may be partly aimed at that. And underneath all of it sits the void's contribution. If we live inside an under-dense region, then the denser universe surrounding the void pulls everything inside it outward, toward the walls, and that outward push adds a coherent, large-scale tilt to the motions of every galaxy in here. Picture a ball sitting inside a shallow bowl. It rolls toward the lowest point, that is, the attractor, the dense region pulling it in. But if the bowl itself is tilted, every ball in it also slides in the direction of the tilt, that is the void, its emptiness setting up an overall slope that biases all the motions one way. The bulk flow is the sum. Galaxies rolling toward local mass concentrations, on top of a whole region sliding down the gradient created by living inside an emptiness. Return to the physics, and the void's role is precisely that gradient, a large-scale imbalance that gives every motion inside it a shared outward lean. The Hubble tension could be a distance ladder error. The galaxy counts could be a brightness bias. But the bulk flows are a measurement of motion, and they show a coherent, large-scale drift exactly of the kind a deep void would produce. When several different anomalies all point toward the same structure, the structure starts to look less like an artifact and more like a real feature of where we live. A skeptic should still push, and the push is real. Measuring bulk flows is truly hard because it requires knowing the distances to enormous numbers of galaxies, and distance errors can fake a flow that is not there. Different teams, using different methods, have reported flows of different sizes, and some find the flows smaller and more consistent with the standard model than others claim. The existence of some bulk flow is not in doubt. The size of it, and whether it truly exceeds what the model allows, is still argued over. This is contested territory, not settled fact. Come back to the scale of the silence for a moment. Hundreds of thousands of galaxies, each a city of hundreds of billions of stars, all sliding together across hundreds of millions of light-years in the same direction, and from inside any one of them, nothing feels like it is moving at all. The flow is enormous and utterly imperceptible. We measure it only by comparing the light of distant galaxies, never by feeling it. An entire river of galaxies, ourselves in it, and not a single ripple any of us can sense. It also deepens the nesting problem from earlier. If our whole region is flowing towards something beyond the Great Attractor, beyond Shapley, then the structures pulling us may be larger than anything we have mapped. Each time we identify what is pulling us, a bigger thing appears behind it. We may be falling toward a concentration of mass we have not yet seen the far side of. What makes bulk flows such a strong test is that they measure something the void story specifically predicts. A void does not just sit there being empty. It sets up a slope, and a slope makes everything inside it drift coherently toward the denser rim. So if we live in a deep void, we should see exactly what we do see: large numbers of galaxies, over huge distances, drifting together rather than scattering randomly. The dense attractor picture alone has trouble producing flows this large over regions this wide. Add the void slope on top, and the size of the flow stops being a puzzle. This is why the flows matter so much to the whole argument. They are an independent line of evidence that does not depend on counting galaxies or measuring the expansion rate, and they point at the same conclusion, that we sit inside a large-scale imbalance, sliding down its gradient along with everything around us. All of this, the void, the flows, our rare address, keeps circling back to a single uncomfortable idea we have been avoiding. For 5 centuries, the rule was that we are nowhere special. But everything we have found says our location is unusual. So, are we, after all, somewhere special? For 500 years, the deepest lesson of astronomy has been a steady demotion. Copernicus took Earth out of the center of the solar system. Later, astronomers found the Sun is an ordinary star, far from the center of an ordinary galaxy, in a universe with no center at all. Each step taught the same thing. We are not special. Our location is typical, and any theory that makes us central should be distrusted on principle. This is the Copernican principle, and it has been one of the most reliable guides in the history of science. The void is the first serious thing in a long time to push back on it. Because if we truly sit deep inside a region 20% below the average density, then our location is not typical. It is unusual, by the model's own measure of unusual. And that creates a real tension with the principle that has served us so well. We trained ourselves never to assume we are special, and now a careful measurement is suggesting that, in at least one specific way, we might be. There are 2 honest ways to hold this, and they pull in opposite directions. The first, take the void at face value. Accept that our location is atypical, and follow the consequences even though they offend a principle we cherish. The danger here is vanity. 5 centuries of being wrong about our own importance should make anyone cautious about a result that flatters us. The second, distrust the void precisely because it makes us special, and assume the apparent uniqueness is an artifact we have not yet uncovered. The danger here is the opposite, refusing to see a real feature of our location, because admitting it feels like backsliding into pre-Copernican pride. The thing is, the Copernican principle was never proven. It is an assumption. And assumptions, however reliable, are exactly the things a careful science has to be willing to question when the data pushes. The void does not overturn the principle, but it does remind us that we are nowhere special, was always a working rule, not a law of nature, and that the universe is under no obligation to honor our humility. Living inside a void does not mean we are at the center of the universe, or chosen, or the point of anything. It means our local conditions are not perfectly representative of the cosmic average, a modest, specific kind of atypical, not a cosmic promotion. The Earth is not the center of the solar system, and learning we live in an underdense region does not put it back there. It just means the patch we measure from is a slightly unusual patch, which is a statement about geography, not about importance. What if living in a quiet, underdense region is not a coincidence but a mild precondition for observers like us? If the calm of a low-density region helps give planetary systems the undisturbed time they need, then beings who arise to ask these questions might be somewhat more likely to find themselves in quieter regions. Under that reading, we are not special by luck. We are in a quiet place, partly because quiet places are where slow, fragile things get the time to develop. That is the anthropic angle, and it neither flatters us nor demotes us. It just notes that observers and their environments are not drawn independently. Two very different claims get tangled here, and they need separating. One is that Earth, or humanity, is cosmically important, chosen, central, the point of the universe. Nothing in any of this supports that, and it is not what living in a void means. The other claim is far more modest, that the particular cubic stretch of space we measure from is not a representative sample of the cosmic average. The first claim is about meaning. The second is about geography. Confusing them is what makes the void sound like a return to pre-Copernican pride, when really, it is only an admission that the place we happen to take our readings is slightly unusual. You can live in an atypical neighborhood without being the center of anything. The void asks us to accept the second, smaller statement, and to stop letting our fear of the first one talk us out of seeing it. A skeptic will rightly warn that anthropic reasoning can explain anything, and therefore risks explaining nothing. That caution is correct, and I do not want to lean on it as an answer. It is a possibility, not a conclusion, a reminder that why are we here might have a partial answer in where could we have been, without that being a full or testable account. The honest position is that we do not know whether our location is a fluke, a mild selection effect, or a sign the model is wrong. This quietly changes the meaning of humility. For centuries, humility meant assuming we are ordinary. But real humility might mean something harder, being willing to follow the measurement even when it says we are not ordinary, without either inflating that into self-importance or denying it out of loyalty to a principle. The universe does not owe us a comfortable position, and it does not owe us an uncomfortable one either. It owes us only the truth, read as carefully as we can manage from where we happen to stand. And where we stand is changing. The void is growing, dark energy is accelerating, and the structures around us are slowly being pulled apart. Whatever our position means now, it will not stay the same. So the next question is about time. If the emptiness keeps expanding, what does the sky look like to whoever is here in the deep future? Dark energy does not just expand the universe. It accelerates the expansion. The rate at which distant galaxies recede from us keeps climbing. And acceleration has a brutal consequence for what we can see. A galaxy receding from us at a certain speed today will be receding faster tomorrow, and faster still after that, until eventually it crosses a threshold where the space between us is stretching faster than its light can travel toward us. Past that point, its light can never reach us again. The galaxy does not vanish. It simply slips beyond the edge of what we can ever observe. This is happening now, slowly. The horizon of what we can see is contracting in terms of content, not in distance, but in how many galaxies remain reachable. One by one, over enormous spans of time, the galaxies outside our gravitationally bound local group are crossing that line, their light stretched and dimmed and finally cut off. In the very deep future, every galaxy that is not bound to us by gravity will have receded beyond reach. The void around us, already vast, will keep growing, and the rest of the cosmos will recede into permanent darkness. Put a timescale on it, even a rough one. This is not a near-future event. It unfolds over tens to hundreds of billions of years, far longer than the current age of the universe. The galaxies will not blink out in any human or even any civilizational time frame. But the direction is set. Given enough time, an observer here will look out and see only the merged remains of our own local group, the Milky Way and its companions, eventually fused into a single galaxy, surrounded by black in every direction, with no other galaxy visible anywhere. A universe of one island in an ocean with no other shores. Now follow the consequence that truly unsettles me. Imagine a civilization that arises in that far future, born into the merged remnant galaxy, looking out at an empty sky. They would have no other galaxies to observe, no way to see that space is expanding, because there would be nothing distant left to measure receding. No cosmic background light bright enough to read, after enough stretching. They could do excellent science, careful and rigorous, and conclude that the universe is a single static galaxy surrounded by eternal void. They would never know the Big Bang happened. They would never know there were ever other galaxies. The expansion that erased the evidence would also erase the record of itself. That is the part that reorganizes how I think about our own moment. We assume the universe has always shown observers roughly what it shows us. It has not, and it will not. The cosmic background light is fading. The galaxies are receding. The evidence we use to reconstruct the entire history of the universe is, on a long enough timescale, a temporary exhibit. We happen to live in the window when the universe is still legible, when there are other galaxies to see, expansion to measure, ancient light to read. A creature born too late would be locked out of cosmology entirely, not through any failure of intelligence, but because the universe will have hidden its own past. The deep future is real, but it is unimaginably distant, and much could change in our understanding of dark energy before then. If dark energy is not perfectly constant, and recent hints, unconfirmed, suggest it might not be, then the far future could differ from the simple accelerating picture. The lonely end is the consequence of one specific assumption about dark energy, and that assumption is exactly the thing we are least sure of. The empty sky is a forecast, not a certainty. Everything we know about the universe's history, that it began hot and dense, that it has been expanding, that there are other galaxies at all, we know because the evidence is still arriving. The ancient light still reaches us. The distant galaxies are still visible, still measurably receding. Run the clock far enough forward and every piece of that evidence is stretched away or dimmed beyond recovery, and a thinking creature could be born into a universe that looks, to every honest instrument, like a single galaxy in an eternal void. They would not be wrong by carelessness. They would be wrong because the universe had quietly retired the evidence. We are not just observers. We are observers who happen to live while the record is still open, and the record will not stay open. We picture the present as ordinary, and the future as where the interesting things happen. But for cosmology, the present is extraordinary, a rare, fleeting interval when the universe is still readable, before the void swallows the evidence. The information we are gathering now is not just knowledge, it is testimony, recorded during the brief age when there is still something to testify about. We are not only living inside an emptiness that bends our measurements, we are living inside an emptiness that is growing, in a universe that is slowly erasing its own history during the one window when we can still read it. How much we have actually managed to read. Of everything the void is doing to us and around us, how much do we truly understand, and how much is still hidden? For all of this, the basic facts of the void are still being argued over. Start with its depth, which sounds like it should be settled and is not. Different studies put the density deficit somewhere between about 15 and 30% below the cosmic average, and they disagree on how far out it extends. That range matters enormously, because a shallower void bends our measurements only a little, while a deeper one could account for much more of the Hubble tension. We do not yet know, with confidence, exactly how empty our own emptiness is. Then there is the question the void was supposed to answer. Does it actually resolve the Hubble tension, or only soften it? Some analyses find a void large and deep enough to explain most of the gap between the local and global expansion rates. Others find it can account for only a fraction, leaving the rest to new physics. The void is either the whole answer, a partial answer, or a distraction from the real one, and serious people hold all three positions. The crisis it was meant to fix may turn out to need a deeper fix. One problem runs underneath all the others, and it is about our simulations. We build enormous computer models of how the universe forms structure, starting from the early conditions and running the standard physics forward. Those simulations struggle to reproduce a void as large and deep as the one we seem to live in. When your best model of how the cosmos builds itself cannot easily make the place you are standing in, that is a signal worth taking seriously. Either the model is missing an ingredient, or our void is a rare draw the simulations would produce if we ran them enough times, or our measurements of the void are overstating it. All three are live, and they cannot all be right. Then the missing matter itself. The void is defined by a deficit, but a deficit relative to what we can count. A real possibility is that some of the missing matter is not missing at all, just in a form we have trouble seeing, like thin, warm gas spread through the void, or dark matter distributed differently than we assume. If the matter is there but hidden, the void might be less empty than the galaxy counts suggest, and some of the anomalies would shrink. We are not certain whether we live in a true desert or merely a region where the water table dropped out of sight. Does the pile of open questions mean the void is not real? No, it means the void is real enough to keep showing up across independent methods, while its exact depth and consequences remain unresolved. A real feature of the universe can be solidly detected and still poorly measured. The uncertainty is about the numbers, not about whether there is something there. This is also where the deepest possibility sits, the one that would dwarf the rest. What if the void is not the problem but a symptom? If our model of how structure forms cannot make our void, and if gravity might behave differently in the low-density reaches, then the void could be pointing at a flaw in general relativity itself, the theory of gravity that underpins all of cosmology. That is the most radical reading. Not that we live in an unusual place, but that the law we use to describe the universe is incomplete, and the void is one of the places where the incompleteness shows. It is far from established, but it is on the table, and the fact that it is on the table is itself remarkable. In most fields, a crisis is bad news. In cosmology right now, it is the most alive the field has been in a generation. A crisis means our measurements have finally gotten precise enough that the universe can disagree with our theories in ways we cannot wave away. The disagreements are not failures. They are the universe telling us, in numbers we can no longer dismiss, that the story is not finished. And being unfinished is the opposite of disappointing. Every one of these open questions is a place where the next real understanding will come from. The void is not a closed case dressed up as a mystery. It is a real edge of knowledge, with our own address sitting right on top of it. The reason simulations struggle to make our void is the cleanest statement of the problem. We can build a universe inside a computer, seed it with the early ripples we measure in the ancient light, and let the standard physics run for 13 billion years. What comes out looks remarkably like the real cosmic web, with filaments, clusters, and voids in roughly the right proportions. But when we ask how often that simulated universe produces a void as large and deep as ours, with observers sitting near its middle, the answer keeps coming back: rarely, or almost never. The simulation builds a universe that matches the sky in general and fails to easily build the specific patch we live in. That mismatch is the whole crisis in miniature. Our best recipe for the universe makes a beautiful cosmos that has trouble including our own front yard. Which leaves one last thing to do. Not to the void out there, but to you, lying in the dark, made of the same matter the void is missing. Start with your own body, right now, in the dark. The matter you are made of was forged inside stars and scattered when they died, long before the sun existed. That matter then gathered into the Milky Way, and the Milky Way settled into a region of space about 20% emptier than the cosmic average. So the atoms in your hand are not just star stuff. They are star stuff that happens to be sitting deep inside one of the largest known holes in the universe. The void is not a distant thing you are looking at. It is the room your atoms are in. Trace what that location has done to everything we tried to measure. The speed of our galaxy, 630 kilometers per second, partly the void pushing us toward its walls. The expansion rate, reading high near 73, partly the void inflating our local view. The age of the universe, the temperature of the oldest light, the coordinated flow of 100,000 galaxies, each one bent, a little or a lot, by the emptiness we sit in. One underdense region, quietly distorting nearly every reading we take of reality. And then the whole story turns around. If we did not live in this void, we might never have stumbled onto the cracks at all. The Hubble tension that hints at new physics, the bulk flows that exceed the model, the clean view of dark energy in the surrounding emptiness, these are visible to us partly because of where we sit. The flaw in our vantage point is also the thing exposing the flaws in our theories. The distortion is teaching us more than a clear view would have. We are not just trapped in a bad seat. We are in the one seat strange enough to reveal that the show itself is not what we thought. A lonely galaxy in a growing emptiness, in a universe slowly erasing its own past. We exist in the narrow window when the universe is still legible, when there are other galaxies to see, ancient light still readable, expansion still measurable. A creature born too early would have found a universe too hot and formless to study. One born too late will find a sky gone dark, the evidence receded beyond reach. We are here in the brief age, when the cosmos can still be read, and we happen to be in a location strange enough to make reading it urgent. Notice what that does to the word castaway. A castaway is stranded, cut off, alone on an island with the sea in every direction. By the long arithmetic of dark energy, that is our fate, our local group, eventually merged into a single galaxy, surrounded by void with no other shore in sight. But a castaway who learns to read the ocean, the stars, the tides, is no longer just stranded. They are an observer of the thing that stranded them. We are the castaways who, before the sea closed in, learned to map the emptiness, who use the very isolation that defines us to measure the universe that produced it. Hold the whole arc in one breath before we let it go. 3 astronomers counting galaxies found our neighborhood running thin. That thinness turned out to push our galaxy, inflate our expansion rate, threaten the age of the universe, chill the oldest light, and bend the motion of 100,000 galaxies around us. It put us in a place the model says should barely exist, gave us the clearest possible view of the force tearing the cosmos apart, and reminded us that the evidence we are reading is on loan from a universe that will one day take it back. Every thread we pulled led back to the same quiet fact. There is less here than there should be, and that absence has shaped everything we can see. The whole is not the backdrop to the story. The whole is the story, and we are the part of it that noticed. So come back to your own chest, rising and falling in the dark. The same expansion stretching the void around us is, on the largest scales, the same physics that governs the light reaching your eyes, the heat leaving your skin, the slow cooling of everything. You are not separate from the cosmology. The faint warmth of your body radiating into the room is the same outward flow of energy, the same arrow of an expanding, cooling universe, running at a scale you can feel. The void is 2 billion light-years across, and it is also right here, in the thinness of the matter your hand is made of, in the dark around your bed. We started by saying you are falling through a hole in space, and nobody told you. Now you know. You are inside it, made of the matter it is short on, riding it outward at 600 kilometers a second toward a wall you will never reach, in a universe that will one day forget it was ever anything but empty. And somehow, in the one window when all of it is still readable, a small, slow, fragile thing inside the hole is the part of the universe that turned around and measured the hole. If we had not been placed in this emptiness, would we ever have found the cracks that are remaking our picture of everything? And does knowing we live inside a vast, growing hole make the universe feel emptier to you? Or, somehow, more astonishing that anything is here to notice it at all? Before the quiet takes over, one last thing, plainly. Thank you for staying. You gave hours of your night to a hole in space 2 billion light-years wide, and to the stubborn project of trying to understand it. That is not a small thing. We are made of the matter the void runs short on, riding outward at 600 kilometers a second, alive in the one brief window when the universe is still readable. And tonight, in the middle of all that vastness, you were here, awake, curious. That counts. So let the numbers settle. The hole will still be there in the morning, and so, I hope, will you, a little more rested. Sleep well. And from one small point inside the great emptiness to another, good night.